All right, so hopefully this will be a quick review over the basics of chemistry, and we'll talk a little bit about why we actually study chemistry in anatomy and physiology. So first, let's talk about what matter is. You should remember this. It's anything that has mass and occupies space. It will have weight, and that's going to be the pull of gravity on mass. The three states of matter: solid, liquids, and gases. Solids have a definite shape and volume. Liquids have a changeable shape but still have a definite volume that can be measured. And gas has a changeable shape and a changeable volume. Energy is basically the capacity to do work or put matter into motion. So you'll remember the types. We have kinetic energy, so like kinesiology, motion, movement. So that's your energy in action. And potential energy, that is stored or inactive energy. You can transfer potential energy to kinetic energy. Think about the example of a roller coaster going up a hill. That is potential energy. When it reaches the top, the higher it goes, the more potential energy it gets to the top, and then now it's going to transfer all that potential energy into kinetic energy as you go down the tracks. So forms of energy, we have chemical energy, which is energy stored in bonds of chemical substances, like think in our bodies as in glucose. Electrical energy is going to be the result of movement of charged particles. You should remember that from physics. Mechanical energy is directly involved in moving matter. So this is the whole idea behind wind turbines. So using the movement and wind to store that mechanical energy. You're taking that kinetic energy and storing it as mechanical energy. And then radiant or electromagnetic energy is energy traveling in waves. So like visible light, ultraviolet light, X-rays, gamma rays, anything on the electromagnetic spectrum. Energy can be converted from one form to another. So like I was just talking about, the whole idea behind wind turbines is that you have that kinetic energy in the wind. When it spins the turbines, then we're transferring that into stored mechanical energy, and then we can actually change that mechanical energy into electric energy by using generators, which will bring power to houses and buildings. Converting between energy is inefficient, so you will always lose some energy as heat, and that's with any kind of energy conversion. So it's kind of like conversion within our bodies. When you talk about the amount of energy whenever you eat certain things, think the trophic levels back to food webs and all that in biology. So composition of matter, we'll talk about elements. Matter is composed of elements. Remember, the most basic thing whenever we're talking about the levels of organization, the most basic unit of life is cells, but cells are made up of organelles, and those individual organelles are made up of compounds, which the compounds are made up of elements. So elements cannot be broken into simpler substances by ordinary chemical methods. And each element, so think about the periodic table, has unique properties. It will have physical properties that you can actually detect, and they'll have chemical properties, which is going to be how they interact with one another. Atoms, these are the unique building blocks for each element. So it gives the element its physical and chemical properties. So when you look at an atom, looking at like the electron shells and how they interact with each other. And these are the smallest particles of an element with properties of that element. The atomic symbol, think about the periodic table. It's 1 or 2 letter chemical shorthand for each element. Talking about elements in the human body, there are 4 elements that make up most of our bodies, and that's going to be, if you remember CHON, carbon, hydrogen, oxygen, and nitrogen, and that does make up about 96%. Then these 9 elements, so calcium, phosphorus, potassium, sulfur, sodium, chlorine, magnesium, iodine, and iron, make up about 3.9% of our body mass. And then we have trace elements. So you have a very, very, very small amount of these. There's 11 elements that actually make up less than 1/100th of a percentage of your actual body mass. Most of them are going to be a part of or help to activate enzymes. Remember, enzymes are proteins that help speed up chemical reactions. So looking at atomic structure, atoms are composed of subatomic particles, protons, neutrons, electrons. The protons and neutrons are found in the nucleus, and the electrons are going to be orbiting the nucleus in the electron cloud. So almost the entire mass of an actual atom is going to be found within the nucleus of the atom. In the nucleus is where you find neutrons and protons. Remember, neutrons are neutral. They have no charge. And their mass, they are 1 atomic mass unit, or 1 AMU. And protons carry a positive charge, so protons are positive. And they are also 1 atomic mass unit. Then in the electron cloud, we have different orbitals within that electron cloud. And these are going to be where the electrons are actually orbiting around the nucleus. We're not going to go into the depths of that like you did in chemistry. They do carry a negative charge, and their mass is so small that it's not considered into the calculation for the atomic mass of an actual atom, because they are 1/2000th the mass of an actual proton. So when you're calculating the mass of an atom or of an element, it is not going to be calculated in there. So it's 0 AMUs, and the number of protons and electrons are always equal. So looking at models of the atom, you have the planetary model, which is very simplified. It is outdated. It's where you'll see a picture on the next slide. You have the nucleus in the center, and then you just have like the rings around it representing the electron paths, but it shows them all as a circular electron path, and they know that is no longer true. Then we have the orbital model, which is the current model used by chemists, where basically it gives where the most probable regions of electron density are going to be, and it's useful for predicting chemical behavior of atoms. And this is where you start getting into the different shapes of the different actual orbits of the electrons. So the picture on the left, looking at the helium atom, this is going to be the planetary model. So you can see that you have, and let me scoot this over so I can get a pen. You can see you have in the nucleus, you have your protons, which are red. Your protons, which are red, and your neutrons, which are yellow, and then you have your electrons orbiting around in the electron shell. And then on the orbital model, you have in the nucleus, you have your protons, which are red, and your neutrons, which are yellow, and then it shows the electron cloud. So it's not necessarily going to be a circular motion like the planetary model shows, like the planets revolving around the sun. Identifying elements. So different elements contain different numbers of subatomic particles. Hydrogen, if you remember, first element on the periodic table has 1 proton, no neutrons, and 1 electron. So remember, the number of protons is going to always equal the number of electrons. Lithium has 3 protons, 4 neutrons, and 3 electrons. Let's see, atomic structure of the 3 smallest atoms. We have hydrogen, helium, and lithium. So this is showing the old school planetary model. And this is showing the different orbital shells. So you can see hydrogen, you have 1 proton, no neutrons, 1 electron. Helium, 2 protons, 2 neutrons, 2 electrons. And lithium, 3 protons, 4 neutrons, so 4 yellows, and 3 electrons. So looking at atomic number and mass number, the atomic number is going to be the number of protons in the nucleus. That is going to be what identifies your actual element. If you change the atomic number, you have now changed the element. And the mass number is the total number of protons and neutrons in the nucleus. So this is the total mass of the atom. And this is written as a superscript to the left of the atomic symbol, whereas the atomic number is listed as written as a subscript. Isotopes, hopefully you remember what isotopes are. Iso means same. So isotopes are going to be structural variations of atoms. It's still going to be the same atom. So it'll have the same number of protons. The only thing that's going to be different is the number of neutrons that they contain. So the atomic number is the same, but it will have a different mass number since it has a different number of neutrons. Atomic weight is the average mass of mass numbers, and these are relative to each other. So whichever ones, hopefully you calculated these in chemistry. So you look at the different isotopes of an atom and look at, you also have to look at their percentage that they exist in nature. And so you take that into account whenever they calculate the average mass numbers of all isotopes of an atom. So identifying elements, atomic number, mass number, and atomic weight. They give the picture of each element, and that allows you to identify the element. So if you know that information, you can identify what element it is. So looking at these three again, so if we were going to look at the atomic mass, looking at hydrogen, you have 1 proton, 0 neutron, so the atomic mass would be 1 AMU. For deuterium, which is an isotope, you're going to have 1 proton and 1 neutron, so it's still hydrogen because of the number of protons that you have, but the atomic mass is going to be 2. And in tritium, you have 1 proton, so it's still hydrogen, but you have 2 neutrons, so the atomic mass is going to be 3. Radioisotopes. So we actually use isotopes in science because we can actually detect them with scanners. So heavy isotopes decompose to more stable forms. Whenever they spontaneously decay, it's called radioactivity. And it is similar to a tiny explosion, and it can transform whatever the original element was into a different element. So we can actually detect these with scanners. So you do use radioisotopes in biological research and in medicine. These radioisotopes, they share the same chemistry as their stable isotopes. Most of the time they're used for diagnosis. So I'll be showing y'all pictures of my daughter had nuclear renal scans whenever she was getting diagnosed for some of her kidney and ureter problems. And basically they inject a nuclear radioactive isotope into your veins, and so as your blood is getting filtered through your kidneys, they actually take images so they can detect those radioisotopes in your body and can actually trace how they get filtered out and filtered through the kidney and out through the ureters and the urine. Radioisotopes do damage living tissue, so they will only use certain kinds, and they use very, very, very small amounts of it. And of course, you've probably all heard of like radiation therapy as far as trying to destroy localized cancers. And in uranium decay, radon, which is formed during uranium decay, actually has been linked to lung cancer. And we'll stop there for now, and I'll continue with matter, molecules, and compounds on another video.